Okay, so let's go ahead and plug in some numbers here just so that we can start making sense of this. And I know it gets a little bit annoying when we solve everything symbolically. So I've replaced the W with a 2 kilonewtons per meter here, 5 meters for the distributed load, and then the distance all the way over to P, which is now 10 kilonewtons, is 8 meters, and the whole length of the beam is now 10 meters. So obviously not drawn perfectly to scale. And so what would we do to find AY and BY? You would draw a free body diagram of the whole thing and then solve for AY and BY. And it turns out that those are BY is 10.5 kilonewtons and AY is equal to 9.5 kilonewtons. So hopefully that's clear for everybody. And now we can start to actually go ahead and put this together and start drawing out our shear bending diagram. So I thought it might be easier, actually, just go ahead and move this all up to here, now that to our constants. And we can see, right, if we start substituting in and rewrite these equations using our now known values. Okay, so for shear between x is 0 to A is now our 5 meters. Then what we have, right, AY is 9.5 kilonewtons minus 2 kilonewtons per meter times x. So this is that shear. This is basically section 1, right? Section 2, again AY, 9.5 kilonewtons minus 2 kilonewtons per meter times A, which is at 5 meters. Right? So that's actually equal to negative 0.5 kilonewtons. And then finally, for section 3, we see that the shear is going to be again AY 9.5 kilonewtons minus the 10 kilonewtons from WA minus the 10 again. So negative 20, negative 11.5. Hopefully I've done that math right. I should double check my slides. Negative 10.5, sorry. Okay, so now let's go ahead and draw that shear diagram. And I've already got our sections set up over here on the right-hand side. So we know that the shear in section 1 is going to start off, if x equals 0, then of course we're at 0 here. Right, so plugging into this equation on the left-hand side, x equals 0, oh, sorry, totally wrong. Then we're going to be at 9.5, sorry, not 0. And now if we plug in for x equals 5, for example, then we should get all the way back down to the constant of negative 0.5. So this is where the shear will end. So again, sorry these graphs aren't drawn to scale, but I think it's more important that you see everything put together. And now we know it's going to be that constant during section 2, right? Shear is not a function of x anymore. And then we drop again, right? In section 3, we have shear is equal to the negative 10.5. So I'll just draw that here on the right-hand side, negative 10.5. Again, not drawn to scale, but the idea is there, right? So that's our shear diagram. Now we can come back and take a look at the moments and see what's going on now that we have these equations set up. I had already started this, so all I've done is taken the free body diagram from the beginning for zone 1 and just repeated it here. And now what I've done is I've replaced this distributed load with a single equivalent force. And I think the only tricky part here is to make sure that you remember that no matter where where you make the cut, the equivalent load is only going to be halfway along the distance. So again, if we take the free body diagram on the top and we see, right, this is our distance x. So the value of the magnitude here is the 2 kilonewton meters times x. Its location, though, is halfway, just like you would for any other distributed load. And so now here I've repeated the shear diagram equation, and we can go ahead and substitute in for AY. We know that that's equal to 9.5 kilonewtons. And now we can write our moment arm equation. So again, sum of moments, m minus v times its moment arm, x times the moment due again to that distributed load here. So its force is 2 kilonewtons per meter times x, and then the x over 2 is the moment arm. And so now we can rearrange and solve for m. And once we substitute in all of our values, here we have that m is equal to 1 kilonewton per meter. I have this x squared, right? Plus Vx. So just bringing everything over to the other side. I know what shear is, a little bit tricky with that linear function. So m is equal to 1 kilonewtons per meter x squared. Shear, I know, I have it right here, right? Is minus 2 kilonewtons per meter. I'm multiplying everything by x. So x squared plus 9.5 kilonewtons times x. So our moment for zone 1 is equal to minus, right, the 1 here minus the 2 here, minus 1 kilonewton per meter x squared plus 9.5 kilonewtons times x. And what kind of function do we have now? We have a quadratic, right? We see that we have an x squared term and then we have x. So if we plug in for x equals 0 for the moment, for this zone 1, here we have 0. Right, so I know it's going to go like this. And then if I took the derivative, I could find out where this peak is, but I'll go ahead and give you the first clue. The peak occurs because of the relationship between the moment and the shear at the point where the shear crosses 0. And so what I'm actually going to have is something kind of like this. So this maxima for this moment is, if I went and did the math, right, and just took the first derivative, on the left-hand side, m prime of section 1, right, you come up with negative 2x plus 9.5, and so on, right? And you'll find and solve for that for x, and it's going to turn out to be exactly where the shear crosses 0. So here it's 22.5 on the right-hand side. What? Can't get my, oh, I'm still in erase mode. 22.5, these are all, of course, in terms of Newton meters. And now I can repeat this process and look at what's happening in zone 2. So here I set up this free body diagram for zone 2, where we have our distributed load acting over the 5 meters. Now all we need to do is start solving for what's going on with the moment in this case. Again, I'll replace this free body diagram by an equivalent one to simplify things. And this time I'll of course include the whole distributed load. So it's 5 kilonewtons per meter, 2 kilonewtons per meter acting over 5 meters. So I'm going to have 10 kilonewtons, a constant now. And its moment arm, right, from this side would be 2.5 meters. Now my value for x comes like this, right? In fact, we can go ahead and rewrite this where we have sum of moments with respect to A. And I can just call this distance x, actually. Right? And so sum of moments with respect to A, I have for the 10 kilonewtons is going to be a negative moment, negative 10 kilonewtons times its moment arm of 2.5 meters. Then m is going to be positive. And then I have the shear, right, And that's acting some distance because we're already past, we're into section 2, right? Its location is going to be, let's call it 5 plus x equals 0. And now if we rewrite this, m equals, bring the shear to the other side, 5 meters plus x, forgot the unit, plus, now go ahead and multiply this out, 25 kilonewton meter. And I already know what shear is, right, from my previous slide, so I'll just substitute that in. So here, shear is a constant. Fortunately, that's easy. Shear is just that negative 0.5 for section 2. And this is 5 meters. This is newtons, probably kilonewtons. Yep. Negative 0.5 kilonewtons. My units are making sense. Plus x plus the 25 kilonewton per meter. And now I have my final equation. I basically have, when I distribute this out, negative 0.5 kilonewtons times x plus 22.5 kilonewton meter. So now my moment on this side is a line, right? I have equation of a line. And again, if we start substituting in, it doesn't matter if you come from the left or the right, you'll get the same answer. These should be continuous functions here. And I have a negative slope. And so if I let x go all the way over to 8, I'll get that the slope actually for m, for x equals 8, I should get that the moment is equal to 21 kilonewtons per meter. So that slope is pretty small. So I'm going to draw that in on the right-hand side. So here's our 21. And then we have one more, right? We can take a look at zone 3 and see what's going on. And here, draw this free body diagram. One more. These problems take a little while to do them fully. Again, AY. I'm going to go ahead and reduce the distributed load. We know that that's going to be that 10 kilonewtons now. And now we're going to add in our 10 kilonewtons for the applied load, normal, shear, and our moment. And what we really want to do is, again, solve for the moment. So I can pick either side. Let's pick this side. We'll call that C. And take some moments about C. And I have M. I still have all these other ones to consider. So the 10 kilonewtons, both of them will generate a positive, right, moment, 10 kilonewtons. And so where's my X now? So in this case, our distances are this, whoops, this is still 2.5. This distance is 8. But with respect to C, and now this is X. So I have 10 kilonewtons. If I take the one on the right, its moment arm is X. And if I take the next one, the one from the distributed load, I have 10 kilonewtons. And that's actually equal to, so this distance is, of course, 5.5. 5.5 plus X. And then I still have the minus AY that I need to consider. So it's getting kind of long. 8 plus X equals 0. And so now if I just do all the algebra, right, I'll write out all the steps. So I have M equals 9.5 kilonewtons. I'm going to start with the AY term, 8 plus X, because I know AY is equal to 9.5, right? We've already defined that. Minus 10 kilonewtons times X. Distribute out the 55, minus 55 kilonewton meter, minus 10 kilonewtons times X again. And start simplifying again. 76 kilonewton times meters. That 8 has a meters attached to it. Plus 9.5 kilonewtons times x minus the 20 kilonewtons times x minus 55. So our final equation for the moment ends up being negative 10.5 kilonewtons times x plus 21 kilonewton meters. And so now when we say if x equals 0, right, what we really mean is that when x is right here, right after that 10 kilonewtons. So in other words, 8 from the left, right, 8 meters. So when x equals 0, then we're still at 21. And if we go all the way over to the right-hand side and let x equal 2, then we're going to get actually 0, right? So if we say m at x equals 0, right, again, look at how we've defined x, that it's acting right after 8, essentially. Then we get that m equals 21 kilonewton meter, sorry. And when x equals 2, we get 0. And so on our shear diagram, this ends up looking like this. So we have a much steeper slope, right, for this equation. And so that's the way you would set up these shear bending diagrams using all of them together. Again, these relationships still are holding, right? We have negative here, positive, right? And what that means is we have a positive increasing moment. Here we have a negative shear, so we have a negative slope, a negative shear, and a negative slope. Next time we'll start talking about the analytical solutions for these and how these are related mathematically. So these aren't just coincidences, but there's actually a mathematical relationship, right? Hopefully you can see how the shear and the bending moments, right, are all integrated together.